Hello, my name is Pallavi Pilaka. I'm in the Introduction to Biochemistry class on Wednesdays from 4 to 4:50. My ID number is 905707824. So today I'm going to talk about the Table 1 from the article titled Turning a Riboflavin Binding Protein into a Self-Sufficient Monooxygenase by Cofactor Redesign. In this article, the author discusses the performance of monooxygenase, which perform selective oxidation reactions for organic substrates. They are also considered to be extremely valuable biocatalysts. The activity of the monooxygenase is often dependent on cofactors, such as NADPH. These cofactors give the oxidizing factor electrons for the process to take place. Scientists have attempted several times to overcome the use of NADPH in the biochemical process. The authors of this article attempt to create a self-sufficient monooxygenase by redesigning an artificial self-sufficient flavoprotein, which acts as the cofactor needed for this process. In this reaction, scientists determined that flavoprotein monooxygenase are able to perform and stabilize intermediates needed for reactions. However, other flavoproteins decay quickly when introduced to solutions. In the past few decades, several scientists have studied several different flavin derivatives. These studies concluded that natural flavin cofactors are not stable in the proxy state. NF5 alkylated flavins can create stable 4A peroxyflavins when they're reacted with hydrogen peroxide. Later studies showed that N-alkylated flavins are powerful oxidizing catalysts. This inspired the authors to come up with a study to determine the self-sufficient monooxygenase by redesigning an artificial self-sufficient flavoprotein. To test the process, the authors of this journal selected RFBP from the chicken, which has no catalytic properties of its own. RFBP is a storage protein and can be isolated from the egg fairly easily. In this study, alkylated riboflavin and lumiflavin derivatives were prepared. The authors succeeded in the incorporation of reduced forms of flavin into the RFBP. We know this because when the protein was combined with the alicase, the protein retained its color. The binding of flavin, too, was determined by the fluorescence of the solution. Scientists refined the tight binding of RFBP and the flavin, which were then tested for their ability to perform peroxide-driven and anti-selective sulfoxidations. The Table 1 in this article discusses the results of these tests. Table 1 shows the excess amount of sulfoxides produced, and in the fourth column, the flavin is numbered according to the type of flavin used. Also, the sulfoxides tested were converted onto a scale of 37 to 55% in the second to last column. In the final column, the authors displayed the yielding of the excess sulfoxides that resulted.